Let's talk about the lattice technique today. First, look at this example. How many different routes are there from the point A to point B by just going north and east? This is the same problem we have discussed before when we learned how to describe a problem using proper counting language. Do you still remember? Try it yourself first. There are totally 10 steps required from point A to point B, among which 6 must go east and the rest 4 must go north. Therefore, this problem is equivalent to selecting 6 eastern-bound steps out of totally 10 choices, which leads to the answer as 10 choose 6 equals 210. Nothing fancy, isn't it? Let's modify the problem a little bit. Now we have a blockage somewhere on the map. No one can pass it en route. How many possible routes are there from point A to B then? Try it yourself. There are several different ways to count. One is to use a complementary technique. Instead of counting how many routes not passing the blockage, let's first count the number of routes that pass it. This new problem can be solved in 2 steps. The first is to count the routes from the point A to the blockage. The second is to count the routes from the blockage to point B. Both of them are a mini version of the previous example. Do you see that? Each has 5 choose 3 possibilities, that is 10 choices. Therefore, by the multiplication principle, the total number of routes that pass that blockage is 10 times 10. We can then subtract it from the total possibilities to find the number of routes that does not pass the blockage. A little bit complicated, but still doable, isn't it? How about these cases then? It's quite easy to create various problems of similar nature by putting different restrictions. But on the other hand, if we have to invent a method to handle each different problem, we are surely in trouble. So the question is there a more general solution? Yes, there is. Let's introduce the lattice technique. It is a very simple but powerful method. Let's say we have 2 blockages on an irregular grid map. Instead of inventing an individualized plan for this, let's just count. How many different ways can lead to here from A? Clearly, it's 1, right? How about this point then? Again, 1. Let's simply mark the number of possible ways that can lead to these points. This one, the only way is where this, so 1 again. Okay, how about this? 2, right? Why? There is one way from here and another way from here. How about this point? 3, correct. 2 ways from the left and 1 way from below. So what pattern can you see? The value of a point equals the sum of the values of a point on its left and the point below. Correct? Why is this? This is simply because the addition principle. There are 2 different cases that can lead to a point, from the left or from the below. Therefore, by the addition principle, the total numbers of ways is their sum. Then we can just simply fill out all the grid till the final destination, the point B. So how to deal with a blockage? Because it is blocked, it has no ways. So this point has the same value as the one on its left. Finally, we get the answer as 74. The idea is pretty simple, right? Take a pause. Make sure you follow the logic before continuing. The lattice method is very flexible, as you can imagine. It can handle various shape, grids, or with different restrictions. Its algorithm is very simple, intuitive, and general. And after you have marked your way towards the destination, you know you get the correct answer. As we have seen before, some problems can be solved using individualized strategies, such as counting the opposite. But probably you may not be so sure whether your answer is correctly or not. With the lattice technique, however, you will be very certain your answer is right if you do not make any silly mistakes. Clearly, there's one obvious drawback of this technique. The calculation will be tedious if the grid is big. Indeed, this is the case. Hence, this technique is ideal for computer software. In fact, it is widely used in many industries, such as the finance industry. Many Wall Street banks use this technique in their pricing softwares. Okay, let's put it in action. This is a challenging problem. Two people come up with a new rule when playing table tennis. Basically, the scores will be simplified in a way a fraction number is simplified. So, for example, the score 2 versus 2 will automatically become 1 versus 1. 6 versus 3 will become 2 versus 1, etc. The question asks how many possibilities are there to finish a game while no such simplification event occurs. This problem is quite lengthy. You can pause the video to read it through and spend a moment to think how you will solve this problem. This problem is very unique and hence it's very difficult to tackle. Here comes the lattice technique. What we can do is to draw a 21 by 21 grid. On this side, we mark from 1 to 21. And on the other side, we do the same. Then each grid represents a possible score. For example, this point means 2 versus 1. Now this problem becomes the same as those problems we have discussed earlier, doesn't it? From the scoring perspective, a game starts from here. The game will finish when it reaches either the top or the right line, depending on which player wins. As we do not want scores like 2 versus 2, such points can be viewed as blockage. By symmetry, we only need to count the top part and then multiply the result by 2. Solving this particular problem is tedious, but it works, right? That is all for this topic. I hope you find it useful. Thank you.